Hello, my name is William Alexander. Today I will be presenting my capstone project titled A Least Cost Path Analysis for High-Speed Railway Development. High-speed railways generally refer to passenger railroads which travel at over 200 kilometers per hour or 120 miles per hour. Rising adoption in much of the developed world aside from the US as an alternative means of transportation from air travel with benefits of cost savings on travel, convenience, and a reduced environmental impact. Purpose of the project is to develop a model that will calculate the most cost-efficient path for development between two major cities. The results will be checked against the plans for a currently in development high-speed rail line between Houston and Dallas, and my model will be refined based on that comparison. The benefits of high-speed rail include the economic, reduces cost of travel compared to air, and it encourages development along the lines. There are social benefits. It can reduce traffic congestion, and there are savings in time compared to car travel. There are environmental benefits. There's reduction of air pollution and reduced petroleum consumption from both the reduction of gasoline for automobiles and jet fuel for airplanes. It is important to keep in mind some limitations of high-speed rail. It is not a magical panacea for transportation infrastructure. There are only a few profitable high-speed rail lines which are outside of Japan. Japan's an anomaly in that most of its network is cost-effective. Studies show that the travel time and costs favor high-speed rail over air travel only up to about 5 hours of car travel, beyond which travelers prefer the convenience of air travel over the costs. There are very high upfront costs to high-speed rail development. A study shows that many Spanish high-speed rail lines are in danger of not paying for themselves over their operability lifetime. To get the most out of high-speed rail, you need to do some planning in advance. Individual lines should aim for a distance of about 200 miles and should try to plan their stations with intermodality in mind. This is the concept that people will more likely adopt a new section of transportation infrastructure if it has good synergy with other aspects of transportation infrastructure. For instance, a high-speed rail route that has a terminus near an airport would mean that people could fly a portion of their journey and then take a high-speed rail line for the rest of their journey, and perhaps the costs will be more favorable to them over just air travel the whole way. But generally speaking, you have to have that option convenient. You can't place the high-speed rail terminus at one end of the city and the airport at the other and expect people to waste an hour traveling between them. And it's also very similar for connecting to local transportation infrastructure. You want your high-speed rail terminus to be by a connection to the local bus network or metro or subway network. That way people don't have to have the inconvenience of having somebody drive them around or getting an Uber over to the subway and such as that. It just encourages the adoption of the high-speed rail network. Now I'll be going into the submodels that will form my total model. So this first submodel is for slope. This is an engineering concern developing large-scale infrastructure. You got to have the slope of the ground in mind. A steeper slope is going to result in higher development costs. To develop my slope model, I first downloaded a set of digital elevation models, and then I merged them together, which is here, and this formed my test area. You can't really tell just from slope, but Houston is around here, Dallas is around here, and you can see how the major rivers form. As the closest that East Texas gets to valleys. This is only a difference on the low end of and between the high end of something like 350 feet over these 200 miles. But uh, it is still the slope, it is still the elevation model for this area. And so from this elevation model, the slopes were calculated between each cell, and they were classified according to natural breaks jinx into 10 groups. With these greener values are a lower value, some ones and twos, where terrain is flattest, and yellows and oranges and reds were assigned to higher values where slopes are greatest. The next model submodel is land cover. Uh, the land cover data set gives a value to each cell corresponding to the terrain type predominant in that cell. So these dark blue ones, for instance, are lakes, where these light blue ones are running water for rivers. Green here are forests, red is urban development, yellow is are plains or shrubbery, and I believe brown was farmland. So at that point, I then reclassified uh, these different terrains into uh, a model between 1 and 10 based on the development cost those land types would add to the project. So, uh, grasslands, plains, farmland, anything that has had obstacles cleared out are favorable. You don't have to do much work to build over them. So those were given a low value, and that's the green over here. Whereas things such as forests that require cutting away land, that's red. That's very high uh, value because it requires a lot of work to clear away the forests. Urban areas, you have to plan around buildings or demolish them or build over roads. So that's higher cost. That's yellow and red over here. And rivers and lakes, got to build a bridge over them. So those are also red. All right, my next two submodels are related to existing infrastructure rather than more engineering concerns based on the land. So this submodel is based on power transmission lines. This is something I incorporated because you save costs in high-speed rail development by developing near to power transmission lines, because high-speed rail needs a power transmission line running over it to power the train. It doesn't run on gas. So the nearer you are to an existing transmission line, the less the cost you have to build a new transmission line over the railroad. And in order to make this model suitable to fit in with the other models, this here is a line model. That's a vector data type. This kind of calculation requires rasters because you're using arithmetic based off of individual cell values. So what I did is I drew buffers at 50 meters, 500 meters, 2.5 kilometers, and 5 kilometers over the power lines. And I gave those different values. I classified them into different values, giving low values, the better values, the cheaper values, to buffer areas that were closer to the power line. And then I converted those polygons into rasters. And that's what this is here. This is a raster over the whole test area that can be added, subtracted, multiplied, or otherwise arithmetically engage with the previous two submodels. And this is a highway submodel. And the logic here is that it is cheaper to develop a railroad closer to a highway because that is where the freight is going to be transported to bring building materials to your build sites. So the closer you are to a highway, the cheaper it is to transport building materials to the railroad. So I did the same thing as with the power transmission lines: buffers, merge, convert into raster here. The weighted overlay is when I added all of these rasters together. Now, the weighted overlay process applies a weight to the values of each cell in multiple rasters. Then you add the values of each cell uh, of the cell in each raster that overlap. Okay, so the overlapping cells in each raster, you add them together into a final raster, which in my case is a cost raster. Maybe I can make this a little more clear. Over here, my example. This is the example of the window you use to create the weighted overlay. So I have my slope model here. I've given it a weight of 50%. That means the value between 1 and 10 that I assign to those slopes, I will take 50% of that value and I will add that to the values of the other models, which themselves have been are only a percentage of whatever weight I apply to them. So in this case, I applied 50% to slope, 30% to land cover. That means I think the cost is going to be based more on slope than on land cover. So if I took out 5, if I have a land cover value of 5, 50% of 5 is 2.5. So I take that 2.5 value, I add it to a land cover. Let's say land cover value was also 5. And I took 30% of that. 30% of 5 is, let me see, I think that's 1.5. So you add that 2.5 to 1.5, you get a total value of 4. And you add that to the other two submodels, maybe you get a total cost value of 4.5. And that is the total cost for that raster. So so it's leaning more towards the original slope value than it is the original land cover value. And so the program does this arithmetic for each cell in the area, and then it will use this as the base layer when calculating paths. This is a model. Rather, this is the model I used. It's broken up into sections. This section is where I merged the digital elevation models and then converted that into a slopes. This is where I handled the buffering, then erasing, and merges for the power lines and for the highways. And somewhere around here I did land cover. This little bit down here, that's a KML to layer function. So this whole thing was going to end up with a comparison to the planned high-speed rail route by Texas Central over between Houston and Dallas. Their map, they have, rather their planned line was in a KML file. So I converted that to an ArcGIS layer in order to compare it in the program with my calculated routes. So this is my result. This is my result map. From here, I ran about a dozen different weights and compared them all. And these are the ones I chose out. Now, this brown line, this is the planned route. So you can see how it comes northwest out of Houston, curves around to the west, comes back in, goes up in a pretty straight line to Grimes Station, which is going to be the station which feeds College Station over here. Proceeds to go, following the straight path, curve around here, goes up to Dallas like this. Now you can see pretty obviously that one path follows it closer than the other paths. That's the orange path. The orange path had weights with equal land cover and slope values. Equal land cover and slope weights, 40% each, with 50% power line weight and a 5% highway weight. I found that in general, once I'd done a few analyses, I overlaid the planned route over my power line and highway models, and I discovered that the high-speed rail route followed power lines mostly. That's what this straight line here is power lines. Same thing, over here. A lot of it's coincident with power lines. So the people planning this route obviously puts more value into being nearer to power lines than into highways. So my solution that does the same, favoring power lines over highways, is what ends up closest to the brown line. I have the blue line here as a comparison of if you didn't include power line and highway weights at all. If it was just slope and land cover equally. You see how it curves out way west, wide of these other routes. So that just goes to show that uh, those may be prime engineering considerations, but they're not the only considerations taken when planning a route like this. And this red route was when power line and highway routes were given highway and power line models were given equal weight. And if you overlay this with my highway model, you'll see that it follows highways a lot more than it does power lines. That's generally what a lot of my different weight values fell into. They either follow the power lines or they follow the highways. So the orange one is what followed the planned route best, except for this leg down here. I believe that the Texas Central did their route this way because this passes through several vacant lots that they've highlighted buildings for. I believe there's going to be support facilities. So that's property they're planning to buy to develop their support facilities. So that's not really a consideration I can take into account in my line. So this here is following the closest power line out of Houston as opposed to going around this way by those vacant lots. There's another deviation here. Like right here is some sort of, I'm not really sure, drained area, maybe a drained reservoir or an old, I don't know, quarry or something. I couldn't find any information on it on Google Maps, but I think there's some kind of interest or danger there that the designers decided to curve around rather than go straight through, but I can't figure out what it was. So my conclusion is, like I said, that orange route with these weights produced the results closest to professional planning. Possible extra sources for additional submodels I could have done with having band areas, such as cemeteries, monuments, active oil and gas leases, environmental restrictions, and building footprints. Some of these data sets I had, I just couldn't make them work out. I ran into a major problem where a lot of these were they had the same field value names, but the data types within those values fields that shared the same name would be different data types. You may have had a string data type versus a float data type for whatever reason. So merging them went very, very ugly, and in the end, I just couldn't make it work out. But most of it was irrelevant anyway because the analysis, the model as is, favors following existing infrastructure, which avoids most of this anyway. So it's something that would have been nice to have in there for completeness, but it would not actually have impacted the final analysis in any way. The exception is the building footprint to make the rail line avoid plowing through existing buildings. I did try to find data for that. I found some, but it was an incompatible data type. I ultimately could not find any open source data for building footprint for Houston and Dallas to be used in my model. If I were, working for a major company that was cooperating with these cities, the cities could probably provide me with that kind of data, and I could incorporate it. But just as a lonely student, I was not able to. Another good thing that would have been good to include would have been line data of existing railroads, which already have existing easements over private property. So a big problem with developing Texas Central's route is they can't use eminent domain because they're all privately funded, and some people are not letting them have easement rights to go over their land. So that's a big brouhaha, and I think that it would be easier to have, if you already have a railroad crossing over your property, you're probably more likely to agree to pay off to expand on that easement just a little bit to incorporate the high speed rail. So that's something I only really thought of when I was coming up with this presentation. So that might have been something nice to include. These are my sources. I used information from the Texas Department of Transportation, from the Homeland Infrastructure Foundation, from the U.S. Geological Survey, and from Esri ArcGIS Online. And these are my research citations. Thank you very much for listening to my presentation.